So I would like first the organizers for this nice conference for invite me and give me this opportunity to represent our works. And also I want to say I'm very happy to give a talk after the talk of Ekaterina Vadimovna. She was my teacher, first teacher of stochastic process. Probably she does not remember because I was not a good student and at the time, but so in any case.
Я помню.
Okay. So I want to say some our recent results on process on so-called processible catastrophes from the point of view of large deviation, but we make this here with this is a joint work with Artem Logachev from the Novosibirsk University. So let me start. What is random processes with catastrophes or processes with catastrophes? Is informally random processes with catastrophes can be represented as a difference between two components. We say the first component is a regular component, and the second one it's a catastrophic component. So here, did you see my mouse here? Did you see this? My pointer?
Yes.
Okay, thank you. This is my regular component, for example, C, and the catastrophic component are represented by the drastic change of the value of the processes here. For example, here it's time of catastrophe, the second time of catastrophe, third time of catastrophe, and so on. This formula becomes the explicit formula for the when we eat the regular component is, for example, some process with independent increment, for example. So if this process is with independent increment, or in our case, we consider the Poisson process, this formula will be exact formula of definition of the process with catastrophe. You see that there are a lot of processes that can be represented in this form. And we started to analyze what is really the process that we can call the catastrophe. What does it mean, the catastrophes for such processes? So the regular component represented by a random process account for random or even non-random regular changes, or we call minor changes such as natural birth and death in a population, income and expenses of a business company, KE dynamics, and so on. Generally, this process is assumed to be non-explosive. Even we can suppose that it can transient, for example, with positive drift, but it's not necessary. In literature, various types of regular processes or regular underlying continuous or discrete time processes are considered, including the death processes, death immigration death, diffusion processes, Poisson processes, but this is our case, generalized renewal processes, even branching processes, and etc. What about the second component? The second component is catastrophic component. It is responsible for the drastic changes, for the major changes in the process that occur at the time of catastrophic event. For example, for changes in population, this could be the mass death due to epidemic or natural disaster, collapse of financial institution, and so on. This component is characterized by the the two things. The first one is the inter-arrival time between catastrophes. I call this tau k, and the sum of tau k, I don't know, Tn. It's instance of catastrophes, and another say tau k, it's independent IED positive random variables for sure, and the second component is the distribution of size of catastrophes. Suppose that at any given position of a process is x, zeta k of x, zeta k of x, it's the size of catastrophes. It's a jump, it's a decrement that the process suffer at the catastrophic moment. So we need to define the distribution of such catastrophes. The size of catastrophes usually differentiated between the total or mild catastrophes, where the total catastrophes, it seems that the process started from zero again. For example, yes, in mild catastrophes, permeates the process started from some point. It can be it's not equal to zero. Some point it can be also the random point. What examples of distribution that is very frequently in literature, various types of catastrophes are often discussed, including reset of total catastrophes. The distribution can be defined with probability 1. If we started with point m, with probability 1, in the next time we will the process will start at 0. This type of catastrophes very useful, very often used in search processes in physics literature, for example. Another example is uniform catastrophes, is also very well studied when if we start from, if our process is at the point x, we choose the next point uniformly in all these interval. Almost uniform catastrophes is some slight modification of uniform catastrophe. Binomial catastrophes also is very popular in the literature, where if especially for the population processes, where x, it means that the size of my population is x, and in an instance of catastrophes, any individual has a positive probability to survive the catastrophes. So it means that my increment in this moment will have a binomial distribution with some parameter p, and m, where m is the size of my population at the instance. Also, well known mentioned geometric catastrophes. This distribution is given by truncated geometry. Do you see?
May I
Yes.
interrupt you? We have a question.
Okay.
You didn't say what is xi-k, xi of t.
Xi of t. Xi of t. It's xi of t. It's sorry. Something wrong with my mouse here. Xi of t, it's the definition of my process. The definition of my process, xi of t. Xi of t, it's we have some regular component, blah, 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 and it's a definition of my process.
Yes, okay, thank you.
Can I ask a
geometric.
question? Can I ask question as
Oh.
well? Sorry.
Okay.
Tole,
Please.
you said M is size of the population, but you previously said that Xi is modeled by transient process, right? So it goes to infinity, right?
Yes, if you see, for example, this process, it's a regular process of underlying processes that we call. It can be transient processes. It can be. It's not exact definition to be
But you assume that population is bounded, but it's M maximal.
No. I don't assume this because M is here. It's only to say that M is a current. Sorry. Here should be
okay,
M. It's a current state of my process.
Understood.
Okay.
Thank
Sorry
you.
for. So here should be M, not X. It's my fault here.
Sorry, and all your processes are integer values.
For example, can be integer values. My process that I will show here, it's with integer values. It can be interpreted as a population dynamic process. But in general, it's not necessary. I know that, for example, it can be Brownian motion. Also, the people consider it as the underlying process. So can be. It's not necessarily integer process. Sergey Anatolyevich, I responded.
Yes, thank you. Okay.
Okay. It can be various things. So, so this is a type of catastrophes, a type of distribution. What I wanted to say that some time ago we started to study these processes, and we are interested in the large deviation for such processes, and for example, in 21 we published the work about the local large deviation principle for Poisson process with catastrophes. And when you study the local large deviation principle, what we need to see, we need to control the probability that my scaled process, for example, here Xi of T is my original process. When I make a scaling for the process where T go to infinity. What we need to control, we need to control to estimate upper bound, upper and lower bound for the probability of a scaled process to stay within some neighborhood of some function f here. So, and what happened? And we realized. We have realized that if the probability of escape on vicinity during a catastrophe is sufficiently high, the distribution characteristic of the size of catastrophe will become irrelevant. So indeed, we try to extend our large deviation result in order to we try to extend our large deviation result for other type of catastrophes. Here we study the uniform catastrophes. Sorry?
Извините, можно еще вопрос? I have another question. Tau K, are they independent of Xi, or what is the structure?
What is
the law
Tau K? Tau K.
Yes.
Tau K. here the tau k, it's the moment of catastrophic event. It's tau k.
Yes,
It's
but
a moment.
How this moment is defined? Does it fall?
For example, here in this particular model that I talking about now, tau k, it's the moment of Ni2. The Ni2 is a Poisson process. So the catastrophic event come by according to Poisson process with say with rate me. Okay. So tau k, it's
independent of eta, independent of anything else.
Yeah. Independent of anything.
Okay, thank
yes,
you.
yes, sure, independent. So and what I wanted to why I'm talking about these things here because we try to apply our result for another type of catastrophes. Here we studied the uniform catastrophes, and we try to extend our large deviation result to other type of catastrophes beyond the uniform case. So we started with binomial catastrophes, and we found that the large deviation principle remained the same. However, when we applied the large deviation technique to geometric catastrophes, we observed that the rate function changed. So the problem arises of extending the class of catastrophes with the same large deviation principle. Okay, so and because now I define explicitly our Poisson process with catastrophe that we're dealing with. Xi is our process with catastrophes is defined by the difference between let Ni1 and Ni2 be two independent Poisson processes with positive rates lambda and me. So lambda, it's Ni1, it's the growing part of process. So and here Ni2 is responsible of the moment of instances of a catastrophes, or Ni2 is responsible for arrival time of catastrophes. Okay, so it's my regular process. So Ni2, it's defined the arrival time of catastrophes. It's also a Poisson process. And what about the size of catastrophes? The size of catastrophes are defined by these three conditions. The first two conditions, it's a simple condition to the distribution of size of catastrophe to be the proper distribution. Yes, the sum should be one and some boundary condition here same. But I wanted to take your attention in the third condition. The third condition, I quantify this tendency, quantify the tendency, the tendency of catastrophic event to drive the trajectory out of away from the epsilon neighborhood. Okay, and this tendency we quantified this condition. So the limit when m go to infinity, the state of the current state of my process when go to infinity, yes, for any m fixed, the probability that the size will be greater than when is equal to 1, when m minuscule minor m go to to infinity. This is our condition, and we believe that this quantification provides a usual characterized a catastrophic event. This should be characteristic of catastrophic event. Okay, so so let's check this condition for the examples here. The set of or total catastrophe, sure, it's okay. See, uniform catastrophe it's itself so okay. Binomial catastrophe, even it's okay for it satisfies this equation. But the geometric catastrophes, for example, it's doesn't satisfy this equation in itself. So from our point of view, from large deviation point of view, the geometric catastrophe is not catastrophe. It's not catastrophic event. It's not catastrophes in C. So because geometric catastrophe is, for example, if you take it satisfies the Kramer condition. Yes, here the people who know about large deviation, classic large deviation theory. If your increment satisfy the Kramer condition, it's okay. We have the classical theory. So and geometric catastrophe does not satisfy our condition. So go ahead. And what the problem we study? We study two problems. We want to see about how the behavior of a maximum of our process, and so we want to study something about the large deviation principle on the phase space. So let me start with to show the result for the maximum. It's resumed in these two theorems. So for any A greater than 1, this ratio is supremum of this ratio. See, it's go to 0. If I take the here B, so here A I change B. If B from 0 to 1. Then the probability of the supremacy is larger than M. It's equal to 1. So what does it mean? It means that we doesn't prove this explicitly, but this maximum it's like the behavior is like a logarithm of t. Or if or probably we can write something that is its behavior. It's like or grid O of log t, probably some function, for example, g of log t, where g should be some slowly varying function, and so on. Okay. And this indirectly confirmed by the finding for the Sisyphus random walk. I am not sure, but I pronounce right Sisyphus the name. So we studied something like the Sisyphus random walk. It's a deterministic part. It's grown. When catastrophe occurs, so the process restarted 0, and after that it started again. The time of catastrophe is here for Sisyphus random walk. It's Poisson process, for example. In any case of Poisson process, they show there exists a result that the maximum of such, the supremum of such process. It's no, it's not supremum. It's expectation of supremum of such process. It behaves exactly as the logarithm t. So because why we guess that our hypothesis is true. See, and two theorems ensure this hypothesis. Yeah. Some question? Another result is about large deviation principle on the phase space. What does it mean in this phase space? It mean that I look for my process only in here in the last time. So it's my process go see, and here in this space time in the phase space I am interested in the large deviation principle. So the family of random variables is okay, satisfies the large deviation principle with normalized function. It's normalized function. It's here psi of t. Psi of t is equal to t. It's a log of probability and so on. The rate function we found the rate explicitly the rate function for our family of random variables. The proof is commonly we try to find upper and lower bound, and it's very technical. It's very technical things. But I want to comment and the proof the following. Our approach is based on analyzing the probability of trajectories that brings the process to this stage. So we analyzed and our proof it's okay. Some the proof is based on analyzing the trajectory that brings my process at the point X. So we prove essentially our proof is based on the to find the optimal trajectory that brings the process to the X. So we have here two behaviors. If X is larger than lambda plus me, lambda and me, remember it's rate of my two Poisson processes. Lambda is responsible for the growth Poisson for the growing part, and me it's responsible to the coming of catastrophes. And if X is greater than lambda plus 1, so the optimal trajectory should be started from 0. It's grow, it's coming on the X. If X is less than lambda plus 1, it means that the optimal trajectory will stay near here, near the 0, and then it's go to the X. It means that in his part, in the growing part, we cannot have essentially we cannot have a lot of catastrophic event. It means that here we have no catastrophic event. In here we have no also the catastrophic events.
I'm sorry, in the previous slide there was another function I of x. Or it is the same function?
I of x is the same function.
The same,
I of x is the same function. I only show to the optimal trajectories to achieve the x.
Thank you.
We have derived the rate function under the three conditions of size of catastrophes. It's lead to expect that the functional local large deviation principle should not depend on specific type of catastrophe. And that the rate functionals should be the same for the different type of catastrophes as well. So for local large deviation principle, or for the large deviation for the local large deviation principle in terms of trajectories. But surprisingly, this is not the case. It's not difficult to understand why. So indeed, let we state what is localized deviation in the functional space, specifically in the texture. Let D is be the space of Cadillac function and keep it with uniform matrix. And we consider the only subset of monotone and absolutely continuous function on, I am not sure the absolutely continuous. Okay, so the monotone function is a subset of D in the interval 0, 1, and such that this function is like something like this in 0, 1, and up to some point s change, it's a 0 C, and after that it go it's some part of monotonic function, increasing monotonic function here. And not so increasing how the infimum of derivative should be greater than greater or equal with lambda. The lambda, remember, it's a rate of Poisson process which is responsible for increasing of my process. So we didn't prove, but it's a remark. See, the family of random processes here, just in terms of trajectories, satisfies the local deviation principle on the set on the set M with normalizing function T, and this is we know how to find the rate function here. Some people here who know the large deviation principle on trajectories of Poisson process, we see that it's part of large of the rate function responsible for Poisson process. So you see, so in this set of monotone function, we have really the local large deviation principle. It means that these limits exist, and it's the same limit. For non-monotone function, if and also for monotone function that does not belong to the set M, remember there is some restriction to the derivative of this. The derivative should be greater than lambda. The rate function will depend on the type of catastrophe. Will depend on the type of catastrophe. I need to know the distribution, specific distribution of catastrophes. But it's not difficult to understand why. This is because for some type of catastrophes, such as uniform catastrophes or binomial catastrophes, there exists a positive probability that the process remains in the epsilon neighborhood of a continuous function. When, for example, a catastrophic in contrast to the case of a total catastrophe, for example, with total catastrophe, there's zero probability to stay at the moment of catastrophe. There is zero probability to stay in an epsilon neighborhood of continuous functions. So it means that for non-monotone function we cannot write such simple formula, and even more, just if I have this rate function for monotone function, it means that I should to obtain our rate function on phase space as the infimum of all trajectories. It really works. It really works here. And I want to finish with the super large deviation principle. Here we will divide the process, our process, by some function phi of t, such that this function grow more rapidly, grow rapidly than t. Grow faster to infinity than the t. For example, t square or something. So in this case, the family of satisfies the large deviation principle. LSOC with normalized function psi should be just 5t times logarithm here, and the rate function is very simple. In this case, it's infinite, or it's exactly identity function for positive x. So here we need not the third condition. It holds for all type of catastrophe when we can what we can imagine. For the super large deviation principle does not fill the specific distribution of catastrophic size. So I think that I finish here. Thank you for your attention. If you have some question, please. Hello.
Thank you. Any questions? Maybe on Zoom.
Okay.
Any questions? Tatjana, do you have question? Yes, we have question.
Ну, это не вижу. Что у меня все закрыло. Yes.
Anatoly, may I ask you, this name on catastrophes, was that your invention or you got it from somewhere?
Okay. Our invention, it's this condition. Because if you see the general definition of catastrophe, it says there are a lot of processes that can satisfy this. Why we should say that this process is of catastrophe? For example,
Sorry, I
Vadim, yes, okay.
I do not question. I think it's a good name. I just only wanted to tell you that there are many processes of such nature, and they are studied
Sure.
So they studied in neuroscience, and I want to say it because, in particular, Vadim Alexandrovich MALYSHEV, he was also participating in one project, but that was really when you were too young to know. That was maybe some 30 years ago. So this type of process are very well known in neuroscience. And I wanted to say also that there are also a process with interaction. So what you call catastrophe, this moment of catastrophe is usually depends on the state of the neighboring processes. So I wanted to ask you, do you have your catastrophe processes for some dependent components or multi?
No, if you say the dependent components of here, for example, if my process stay in the state X.
No, if you have multi-dimensional process, you have only one side.
Multi-dimensional process. Multi-dimensional processes we didn't study the large deviation principle, but I think that sure it should exist the multi-dimensional processes of catastrophes.
So I suggest you can check some literature. There were some studies.
No, I'm sure. There exists.
I don't know whether Alexander is online, but he was also working on that.
Okay, yeah. It's there are a lot of processes. The only our point it's to define what is a really catastrophic event. What is the catastrophe? And because the geometric part, if you see here geometric part, it's not a catastrophe for our point of view now. So
it is nice analogy. I agree, and I also should say that I did not see large deviations for this process. That was studied something else.
Okay. So, okay. Thank you for your attention.